What if everything you've ever known, the stars, the galaxies, even the very fabric of space and time, was nothing more than lines of code in an unfathomably advanced simulation? It sounds like science fiction, but some of the brightest minds in physics and philosophy have seriously considered this possibility. Picture this: you're standing at the edge of the universe, gazing into the infinite void, when a chilling realization dawns on you. The boundaries of reality might not be what they seem. The cosmos could have edges, not in the way we traditionally imagine, but as the limits of a grand, intricate simulation. This isn't just a wild thought experiment, it's a theory that forces us to question the very nature of existence. Think about the last time you played a video game. The worlds inside those games have edges too, invisible walls, glitches, or seams where the programmed reality ends. Now scale that up to the size of the universe. What if the edges of our cosmos are similarly constructed, not by physical laws, but by the parameters of a simulation? Scientists have even proposed ways to test this idea, searching for potential glitches in the fabric of reality, tiny irregularities in the laws of physics that might hint at a digital framework beneath it all. From strange quantum behaviors to unexplained cosmic anomalies, the clues are out there, waiting to be pieced together. But here's where it gets even more fascinating. If we are inside a simulation, who created it? And why? Are we merely characters in some advanced civilization's experiment? Or is there something deeper at play? These questions blur the lines between science and philosophy, taking us on a journey that stretches from the frontiers of astrophysics to the limits of human imagination. In this video, we'll explore the cutting-edge theories, the mind-bending evidence, and the profound implications of living in a simulated universe. By the end, you might just find yourself looking at the night sky and reality itself in a whole new way. So let's dive in, because the truth could be stranger than anything we've ever dreamed. The simulation hypothesis isn't just a modern fascination. It's a concept with roots stretching back centuries. Ancient philosophers pondered whether reality might be an illusion, but today's version of the idea is backed by startling scientific reasoning. Nick Bostrom's seminal paper laid the groundwork, arguing that if civilizations advance far enough, they'd likely create countless simulations of their ancestors. Statistically, the odds would then favor us being inside one of those simulations rather than the original reality. Elon Musk famously took this further, suggesting the chance we're in base reality is 1 in billions. But what does that actually imply for the universe we perceive? If our cosmos is a simulation, its edges wouldn't behave like physical barriers. Instead, they might resemble the edge of a digital map in a video game, a place where the program stops rendering or where processing power hits its limit. Think of it like a computer struggling to load an open-world environment. Distant stars might not just fade into darkness but could glitch or repeat patterns, revealing the underlying code. Some physicists speculate that these cosmic edges could even exhibit pixelation, a subtle grid-like structure in spacetime itself, detectable if we knew where to look. The very laws of physics might start to break down at these boundaries, behaving more like software rules than immutable truths. This isn't just speculation. Scientists have proposed real-world tests for the simulation hypothesis. One approach examines high-energy cosmic rays. If the universe is digital, there might be a finite resolution to reality, a smallest possible pixel of space or time. At extreme energies, particles could reveal this granularity, like a digital image breaking apart when zoomed in too far. Another clue could lie in quantum mechanics, where particles behave in ways that defy classical logic. Could their strangeness be a sign of optimized processing, like a simulation conserving resources by only rendering details when observed? Even mathematical constants, like the speed of light, might not be fundamental but programmed parameters variables in an equation we're only beginning to decode. Yet the most haunting question isn't how the simulation works, but why it exists. Are we part of some grand experiment, a historical recreation, or even entertainment for beings we can't comprehend? The answers could redefine not just science but philosophy, ethics, and our very sense of purpose. If the universe has edges, they might not be the end of our journey, but the beginning of a far deeper mystery. One of the most compelling clues that our universe might be simulated comes from the very fabric of reality itself, space and time. Just like a digital screen is made of tiny pixels, some physicists theorize that spacetime could have a fundamental granularity, a smallest possible unit beyond which nothing can be divided. This idea isn't just speculative, it emerges from attempts to reconcile quantum mechanics with general relativity, two pillars of modern physics that stubbornly refuse to fit together neatly. If spacetime is pixelated, it would mean the universe operates on a kind of cosmic resolution limit, where smooth curves and infinite precision simply don't exist at the tiniest scales. Imagine zooming in on a photograph until you see the individual pixels. In our universe, these hypothetical pixels would be unimaginably small, far beyond our current ability to measure. But at the edges of existence, where the simulation's processing power might strain, these building blocks could become apparent. Think of it like a video game struggling to render distant objects. Textures blur, patterns repeat, and edges glitch. If our cosmos has similar limits, the boundaries of the universe might not just fade into darkness, they could flicker with digital artifacts, revealing the underlying code. Some researchers even suggest that high-energy cosmic rays, particles traveling from the farthest reaches of space, might carry traces of this pixelation. If they behave in unexpected ways at extreme energies, it could be a sign that they're bumping up against the simulation's resolution. The implications are staggering. A pixelated universe would mean that what we perceive as the smooth, continuous fabric of reality is actually a finely woven illusion. The laws of physics wouldn't be fundamental truths but programmed rules designed to create a convincing experience. This could explain some of the strangest quirks of quantum mechanics, like how particles seem to choose their states only when observed. In a simulation, it would be efficient to render details only when needed, conserving processing power. Even the speed of light might not be an unbreakable barrier but a built-in limit to prevent the system from overloading. But how would we ever detect such a grid-like structure? Some experiments are already searching for signs. Gravitational wave detectors, which listen to the ripples in spacetime from colliding black holes, could uncover minute irregularities if spacetime isn't perfectly smooth. Quantum physicists are also studying whether the behavior of particles at ultra-small scales deviates from predictions, hinting at a digital framework. If these efforts succeed, we might find ourselves staring at the first hard evidence that reality isn't what it seems, that we're living in a constructed universe with edges defined not by physics, but by the limits of an unfathomable computer. What's fascinating is that this idea bridges the gap between science and something almost artistic. A simulated universe would be the ultimate creative act, a masterpiece of engineering so advanced it generates its own conscious observers. And if we're part of that simulation, the pixels of reality aren't just clues, they're brushstrokes in a canvas larger than we can comprehend. The question isn't just whether we'll find them, but what it means if we do. Would it change how we see ourselves, our place in the cosmos, or even the nature of existence itself? the answers might be hidden in the smallest details, waiting at the edges of perception. If simulations follow the same rules as the technology we've built, then glitches aren't just possible, they're inevitable. Every programmer knows that even the most sophisticated software has unexpected behaviors, tiny cracks in the code where reality stutters. Now apply that thinking to our universe, those bizarre quantum behaviors scientists struggle to explain, particles communicating instantly across light years through entanglement. Cosmic rays with energies that defy known physics. These might not be mysteries waiting to be solved, they could be bugs in the system, subtle hints that we're living in a constructed reality. Take quantum entanglement, often called spooky action at a distance. When two particles become entangled, measuring one instantly determines the state of the other, no matter how far apart they are. Einstein famously hated this idea because it seemed to break the universe's speed limit, the speed of light. But in a simulation, this spookiness makes perfect sense. Think of it like two characters in a video game sharing the same variable in the code. Change one, and the other updates immediately because they're linked at the programming level, not through physical space. The simulation doesn't need to send a signal between them, it just updates both simultaneously because that's how the software works. Cosmic rays present another tantalizing clue. Some of these high-energy particles arrive with energies so extreme that they shouldn't exist under our current understanding of physics. Dubbed "oh my god" particles, they carry the kinetic energy of a baseball pitch compressed into a single subatomic particle. In a simulated universe, these could be rounding errors, instances where the simulation's calculations briefly overflow, creating impossible values before the system corrects itself. Just like a calculator might display E when you divide by 0, these cosmic anomalies might be the universe's way of saying, this value exceeds available memory. The edges of the cosmos could be where these glitches multiply. Picture a video game rendering distant terrain. As you approach the map's edge, textures stretch unnaturally, objects pop in and out, and physics starts behaving erratically. If our universe has similar boundaries, they might not be empty voids but zones where the simulation's rules strain under the complexity. Distant galaxies could exhibit repeating patterns, like copied and pasted assets in a game world. The cosmic microwave background, the afterglow of the Big Bang, might contain anomalies that resemble compression artifacts, subtle fingerprints of a universe rendered on finite hardware. Some scientists are actively hunting for these digital fingerprints. One approach analyzes whether the universe has a preferred direction or axis, something that shouldn't exist in an isotropic, natural cosmos, but might emerge in a simulation with processing constraints. Others examine whether high-energy particles exhibit unexpected behaviors that could reveal an underlying lattice structure to spacetime. Even the mathematical perfection of physical constants raises eyebrows. Why do forces like gravity and electromagnetism balance so precisely to allow for life? In a simulation, these could be carefully tuned parameters, dialed in by the creators to generate a stable, observable universe. But here's the twist. If we do find irrefutable evidence of a glitch, does that mean we can hack the system? Theoretical physicist Silas Bean proposed that simulated beings might discover their reality by detecting anomalies in the energy distributions of particles, a kind of cosmic cheat code. It's a dizzying thought. The same glitches that reveal our artificial origins might also become tools to reshape them. After all, every simulation has its debug mode. The question is whether we're players in this universe or its programmers in waiting. Mathematics doesn't just describe our universe, it defines it with an eerie precision that borders on perfection. The gravitational pull between two stars, the spiraling patterns of galaxies, even the way light bends around massive objects, all of it follows mathematical equations with pinpoint accuracy. But what if that's not a feature of nature but a signature of design? In a simulated reality, math wouldn't just be the language we use to understand the cosmos. It would be the framework the simulation runs on, the very code that constructs existence. Consider how video games rely on physics engines, sets of mathematical rules that dictate how objects move, collide, and interact. These systems are flawless until they're pushed beyond their limits, revealing the artificial seams beneath. Our universe might operate the same way. The edges of the cosmos could be where the equations start to stutter, where the simulation's processing power can no longer maintain the illusion of infinite smoothness. Imagine a glitch in a game where numbers overflow, causing a character to clip through a wall or a texture to stretch into oblivion. Now scale that up to cosmic proportions. Distant quasars emitting energy in impossible patterns, or black holes behaving in ways that defy Einstein's equations, might not be anomalies. They could be the universe's version of an error message. Even more intriguing is the idea that certain mathematical constants like pi or the fine structure constant might not be fundamental truths but carefully chosen parameters. In a simulation, these numbers would be variables set by the programmers to create a stable, observable universe. Change them slightly, and reality as we know it could unravel. It's like tweaking the gravity value in a game's code adjusted too much, and characters either float away or collapse under their own weight. The fact that our constants are so finely tuned for complexity and life has led some scientists to wonder, are these numbers evidence of intentional calibration? Theoretical physicist Max Tegmark takes this further, proposing that our universe isn't just described by math, it is math. In his mathematical universe hypothesis, reality is a purely mathematical structure, and what we perceive as physics is just the relationships between numbers. If true, this would make our cosmos indistinguishable from a simulation running on mathematical rules. The edges of such a universe wouldn't be physical barriers but computational ones, places where the equations can no longer sustain coherent outputs, where the logic of the system frays at the seams. So how do we test this? One clue might lie in the way math breaks down at extremes. At the singularity of a black hole, for example, equations spit out infinities, a clear sign that our models fail. In a simulated reality, these infinities could be the equivalent of a divide by zero error, a point where the program simply can't compute an answer. Similarly, quantum mechanics thrives on probabilities, not certainties. Could this uncertainty be a feature of the simulation only resolving outcomes when observed, like a game rendering graphics only when a player looks at them? The deeper we dig, the more math seems less like a tool and more like a blueprint, a set of instructions woven into the fabric of reality. If that's true, then the edges of the universe might not just be the end of space, but the edge of the code itself, a boundary where the numbers stop making sense. And if we ever reach those edges, we might not find darkness or emptiness, but something far stranger, the unfiltered syntax of existence waiting to be read. The universe has a peculiar secret. No matter which direction you look, the cosmos appears almost identical. Distant regions billions of light years apart share the same temperature, density, and structure, as if perfectly coordinated. This uniformity, known as the horizon problem, defies conventional explanation. After all, these regions were too far apart to ever interact, even in the early universe. So how could they possibly sync up? One radical answer lies in the simulation hypothesis. What if this uniformity isn't natural but engineered? Picture a video game rendering a vast open world. To save processing power, developers reuse textures, assets, and environmental details, copying and pasting the same mountain range or forest across the map. From a distance, everything looks unique, but up close you might spot repeating patterns. Now imagine the universe operates the same way. The cosmic microwave background, the faint glow left over from the Big Bang, shows near-perfect uniformity across the sky. In a simulation, this could be a rendering shortcut, a way to conserve resources by recycling the same basic template rather than generating entirely unique regions. At the edges of the cosmos, though, this illusion might start to unravel. Just as a game's terrain glitches when pushed beyond its limits, the universe's uniformity could falter where the simulation strains to maintain consistency. Distant galaxies might exhibit strange symmetries, like reflections in a mirror or subtle repetitions in their arrangement. Even more telling, the cosmic microwave background, often called the universe's baby picture, could contain faint stitching artifacts, patches where the simulation's algorithms failed to perfectly blend the seams. Some researchers have already scoured this ancient light for anomalies, searching for unnatural patterns that might betray a digital origin. The horizon problem isn't the only clue pointing this way. Inflation theory, the leading explanation for cosmic uniformity, suggests the universe expanded faster than light in its first moments, a fix that feels almost like a patch to make observations fit the model. In a simulation, such rapid expansion could simply be a loading mechanism, a way to quickly generate a playable area before fine-tuning the details. Think of it like a game streaming assets as you move, creating the illusion of a seamless world while hiding the fact that most of it isn't fully rendered yet. What's fascinating is that this idea turns a cosmic mystery into a potential design feature. The universe's uniformity might not be a puzzle to solve, but a signature of optimization, evidence that reality, at its core, runs on rules not so different from our own computers. And if that's true, then the edges of existence might be where the facade wears thinnest, where the simulation's shortcuts become visible to those who know where to look. The question isn't just whether we'll find these seams, but what they'll tell us about the nature of the code we're living in. One of the most fundamental rules of our universe, the speed of light, might not be a law of nature at all, but a built-in limit of the system. Think about it, in any simulation, processing power isn't infinite. Data can only travel so fast before the system starts to lag. Now imagine that same principle applied to reality itself. The speed of light, 300,000 kilometers per second, could be the cosmic equivalent of a processing speed cap, the maximum rate at which the simulation can update information across its vast digital landscape. This idea flips everything we know about physics on its head. Light speed isn't just a barrier, it's the universe's refresh rate. Just like a video game struggles to render distant objects in real time, the edges of our cosmos might exhibit strange distortions where this limit strains under the load. Picture a character in a game running too fast for the engine to keep up. The world around them blurs, textures pop in late, and physics glitches out. Now scale that up to the size of the universe, at the farthest reaches of space where the simulation's processing load would be most intense. We might find anomalies like light bending in impossible ways or time appearing to stutter. Even more intriguing is what happens when particles approach this speed limit. As objects accelerate toward light speed, their energy skyrockets while time for them slows down, a phenomenon called time dilation. In a simulation, this could be a failsafe to prevent system overload. Think of it like throttling a computer's performance to avoid a crash. The closer something gets to the maximum processing speed, the more the simulation slows it down to maintain stability. This wouldn't just explain why nothing can exceed light speed. It would reveal light speed as a carefully programmed boundary, not an unbreakable law. Some physicists speculate that at the universe's edges, where the simulation's resources are stretched thinnest, this limit might start to crack. Light from distant galaxies could arrive with subtle inconsistencies, delays, shifts in wavelength, or even gaps in data, like a corrupted video stream. These wouldn't be random errors but systematic flaws, revealing the underlying architecture. Even black holes, with their extreme gravitational pull, might act like cosmic buffer zones, regions where the simulation offloads excess data to prevent lag elsewhere. Their event horizons could be the equivalent of a loading screen, masking the point where the system stops rendering entirely. The implications are staggering. If the speed of light is a processing limit, then the entire universe operates like a carefully optimized program, balancing performance and fidelity. Every star, every planet, every atom is part of a vast calculation running in real time. And just like any piece of software, it has its limits, edges where the code shows through. The question isn't just whether we can find these edges, but what happens if we reach them. Do they mark the end of the simulation, or are they gateways to something deeper, the raw code of existence itself? Dark matter and dark energy, these invisible forces, make up over 95% of the universe's total mass and energy. Yet we can't see them, touch them, or even fully explain them. They're the cosmic equivalent of placeholder text in a document, filling gaps, stabilizing structures, and making the math work. But what if that's exactly what they are? In a simulated reality, dark matter could be the universe's way of padding out regions it hasn't fully rendered, while dark energy might be an algorithm stretching the boundaries to keep the simulation running smoothly. Think of it like a video game loading distant terrain. As you move through the world, the game prioritizes rendering the immediate area, leaving far-off landscapes fuzzy or filled with low-detail stand-ins until you get closer. Dark matter's gravitational pull, holding galaxies together despite their visible stars' insufficient mass, could serve a similar purpose, acting as temporary scaffolding until the simulation decides whether to fully render those regions. Meanwhile, dark energy's mysterious role in accelerating the universe's expansion might be a background process, ensuring the cosmic map doesn't collapse under its own complexity. At the edges of the cosmos, these placeholders could start to glitch. Dark matter's influence might weaken or fluctuate, like a game struggling to apply physics to objects beyond its draw distance. Galaxies near these boundaries could drift apart unnaturally, their motions no longer anchored by the usual invisible hand. Dark energy, too, might behave erratically, speeding up or slowing down in patches, as if the simulation's expansion algorithm is hitting its limits. These wouldn't be random errors but systematic failures, revealing where the code strains to maintain the illusion of a seamless universe. Some scientists have already noticed oddities that fit this idea. Certain dwarf galaxies, for instance, orbit larger ones in ways that defy predictions based on dark matter's expected distribution. Others have found regions where the cosmic microwave background's temperature variations don't align with standard models. Could these be areas where the simulation's placeholder data starts to fray? Even more tantalizing are observations of ultra-diffuse galaxies, ghostly collections of stars with almost no dark matter at all. In a simulated cosmos, these might be zones where the rendering skipped a step, leaving gaps in the underlying framework. The implications stretch beyond astronomy. If dark matter and energy are procedural tools, then the universe isn't just expanding, it's being generated on the fly, with these forces as the invisible code keeping everything in balance. The edges we're searching for might not be physical walls but computational thresholds, places where the simulation's resources thin out and its shortcuts become visible. Finding them wouldn't just solve a cosmic mystery, it would crack open the blueprint of reality itself. The Fermi Paradox has haunted scientists for decades. If the universe is so vast and ancient, why does it feel so empty? Where are the alien civilizations that should have spread across the cosmos by now? One unsettling answer emerges if we're living in a simulation. The silence isn't a mystery, but a design choice. Think of it like a video game set in a sprawling open world. The developers don't populate every inch of the map with characters that would strain the system. Instead, they focus resources on the player's immediate surroundings, leaving distant regions barren or filled with low-detail stand-ins. In a simulated universe, the same principle could apply. Advanced civilizations might not exist beyond our observational reach because the simulation simply hasn't rendered them. They're not hidden there unprocessed, like terrain in a game that only loads when you get close enough. This would explain why our telescopes see countless stars but no signs of extraterrestrial engineering. The simulation's edge, where processing power wanes, could be a literal horizon for life, a boundary beyond which civilizations are either simplified to basic algorithms or omitted entirely to conserve resources. But what about closer to home? If other intelligent species are rare or absent in our cosmic neighborhood, they might function like non-player characters, scripted entities designed to give the illusion of a populated universe without the computational burden of full consciousness. Ancient myths of gods or visitors from the stars could even be echoes of these NPCs, brief interactions programmed to nudge human development without requiring persistent simulation. The Great Filter, a hypothetical barrier preventing life from reaching interstellar scales, might not be a natural phenomenon but a deliberate constraint to keep the simulation manageable. There's a chilling elegance to this idea. The Fermi Paradox isn't a puzzle to solve, it's a feature of the system. The eerie silence of the cosmos, the absence of alien megastructures, even the way life seems perfectly balanced on a knife's edge, all of it could point to a universe optimized for human observation, nothing more. The edges of reality wouldn't just mark the end of space, but the limits of our significance. Beyond them, the simulation might not bother generating answers to questions we're not meant to ask. Quantum mechanics has a peculiar habit of keeping reality in limbo until someone looks. Particles exist in a haze of probabilities, their properties undefined until the moment they're measured, a phenomenon so baffling that even Einstein called it spooky. But what if this indeterminacy isn't a quirk of nature, but a feature of the system? In a simulated universe, rendering every particle state in real time would be computationally wasteful. Instead, the system might employ a clever optimization, only calculating the specifics when an observer demands them. It's like a video game that doesn't bother rendering the details of a distant mountain until you train your telescope on it. Why waste resources on something no one's checking? This lazy loading approach would explain why quantum particles seem to hover in superposition, their properties unresolved until observation forces a decision. The famous double-slit experiment, where particles act as waves when unobserved but snap into particle-like behavior the moment they're measured, could be the simulation's way of conserving processing power. Think of it like a streaming service adjusting video quality based on your internet speed when no one's watching. It keeps things fuzzy to save bandwidth. But at the edges of the universe where the simulation's resources stretch thin, this optimization might start to glitch. Imagine approaching the cosmic horizon, where the fabric of spacetime itself begins to fray. Here, quantum particles might not just resist observation. They could behave erratically, flickering between states like a corrupted file struggling to load. Entangled particle, usually perfectly synchronized no matter the distance, might desync near these boundaries, their spooky connection faltering as the simulation fails to maintain coherence. Even the vacuum of space, usually teeming with virtual particles popping in and out of existence, could grow unnaturally quiet, as if the background processes have been put on pause to free up memory. Some experiments already hint at these limits. Quantum systems in lab settings occasionally produce results that deviate slightly from theoretical predictions, tiny discrepancies often dismissed as noise. But what if these are actually rendering artifacts, moments where the simulation's calculations lag or skip a step? At the universe's edges, these anomalies could multiply, revealing the underlying framework. Particles might leave faint digital fingerprints, unexpected energy spikes, or probabilities that don't quite add up, like a pixelated texture seen up close. The deeper implication is staggering. If quantum uncertainty is a performance hack, then reality isn't just stranger than we imagine, it's stranger because it's designed. Every time an electron chooses a path, or a photon decides to be a wave or particle, we might be glimpsing the universe's source code in action. And at the edges, where the simulation's optimizations break down, we could find the ultimate debug screen, a place where the variables stop pretending and the raw math of existence bleeds through. The Big Bang wasn't just the birth of our universe. It might have been the moment the simulation booted up. Think about what happens when you power on a computer. Lines of code execute in a precise sequence, memory allocates, and systems initialize until the operating environment stabilizes. Now imagine that process scaled up to cosmic proportions. The initial singularity, a point of infinite density, could be the equivalent of hitting the start button, triggering a cascade of processes that generated space-time, matter, and the very laws of physics as we know them. If this analogy holds, then the edges of the universe might not just be physical boundaries, they could be the frontiers where the simulation's startup routines are still unfolding, trailing behind like a loading bar stuck at 99%. Clues to this cosmic initialization might hide in the universe's oldest light, the cosmic microwave background. This afterglow of the Big Bang isn't perfectly uniform. It contains faint temperature variations, like fingerprints left by the early universe's turbulent energy. In a simulated reality, these imperfections could be the equivalent of system logs, recording how resources were allocated during startup. Some patches might be hotter or colder, not because of random quantum fluctuations, but because the simulation prioritized certain regions for rendering first, leaving others to initialize later. At the very edges of the cosmos, where the simulation's processes are most strained, these anomalies could become extreme zones where the background radiation flickers unpredictably, like a screen struggling to display a corrupted file. Even more telling are the universe's fundamental constants, the precise values that dictate gravity, electromagnetism, and the strength of nuclear forces. These numbers are so finely tuned that altering them by even a fraction would render life impossible. In a simulation, this precision could reflect careful calibration during the boot-up sequence, like a programmer setting initial parameters to ensure stability. The edges of the universe, where initialization might still be incomplete, could reveal these constants in flux, places where gravity weakens inexplicably or light bends at angles that defy Einstein's equations. It's as if we're glimpsing the simulation's configuration files mid-edit, watching the universe debug itself in real time. What's haunting is that this idea turns cosmology into a kind of cosmic forensics. The Big Bang wasn't just an event, it was a process, and we might still be living through its aftermath. The furthest reaches of space could be where the simulation's initialization scripts are still executing, their energy signatures bleeding into our observations as ghostly anomalies. If we learned to read those signatures, we wouldn't just be studying the universe's origins, we'd be reverse engineering the very code that brought it into being. Time doesn't just pass uniformly across the cosmos, it bends, stretches, and even crawls to a near halt under extreme conditions. Near black holes where gravity warps spacetime into knots, clocks tick slower compared to those in empty space. But what if this phenomenon isn't just a quirk of gravity? In a simulated universe, time dilation could be a telltale sign of computational strain, a way for the system to manage its resources when processing demands spike. The edges of the cosmos, where the simulation's framework might fray under complexity, could be where time itself starts to stutter like a lagging computer struggling to render an overloaded scene. Imagine a video game engine straining to handle too many characters on screen at once. To prevent crashing, it might slow down time, reducing the number of calculations per second to keep things running. Now picture the universe doing the same, at its farthest reaches where the simulation's processing load would be most intense. Time might not just dilate, it could fracture. Light from distant galaxies might arrive with inconsistent timestamps, as if the fabric of reality itself were buffering. Clocks on hypothetical probes near these edges could tick erratically, speeding up or slowing down without the influence of any visible mass, revealing not the hand of gravity but the limits of an underlying processor. This idea isn't pure speculation. Astronomers already observe time dilation in extreme environments, like quasars billions of light years away, where the universe's expansion stretches light into longer, redder wavelengths. But in a simulation, this redshift might not just be from cosmic stretching. It could be a rendering artifact, a sign that the program is struggling to maintain real-time consistency across vast distances. Even more telling would be anomalies in pulsars, the universe's natural timekeepers. These spinning neutron stars emit radio waves with metronomic precision, but near the cosmic horizon, their rhythms might waver unpredictably, like a skipping record. If scientists detected patterns that couldn't be explained by relativity alone, it might hint at something deeper, a system prioritizing certain regions over others to conserve processing power. The implications reach beyond astronomy. If time dilation at the edges isn't gravitational but computational, it would mean the universe isn't just governed by laws, it's managed by them. The speed of light, the behavior of black holes, even the arrow of time itself could be features of an optimization strategy, not fundamental truths. And just like any overloaded server, the cosmos might have its own way of displaying an error message, not in pop-ups or crashes, but in the subtle, creeping distortions of time where the simulation seams begin to show. What's truly mind-bending is that these distortions wouldn't just be flaws, they'd be clues. By mapping where time stumbles, we might not just find the edges of the universe, but the edges of the code that built it. The ultimate clock isn't ticking down to the end of reality. It's counting up to the moment we finally understand what's on the other side. One of the most radical ideas in modern physics suggests that our three-dimensional universe might be nothing more than an elaborate illusion, a holographic projection encoded on a distant two-dimensional surface. This isn't science fiction. It's a serious theory born from studying black holes and the strange behavior of information at quantum scales. If true, the edges of our cosmos could be where this grand illusion starts to unravel, revealing the flat, pixel-like code that underpins everything we perceive as reality. Think of it like a movie projected onto a screen. The images appear to have depth and motion, but they're actually flat, flickering patterns of light. In the same way, our universe's vast galaxies, swirling nebulae, and even our own bodies might be shadows cast by information etched onto a cosmic horizon far beyond our reach. The holographic principle takes this further, proposing that every event inside the universe, every collision of particles, every birth of a star, is just data playing out on this unimaginably distant surface. At the edges of existence, where the projection frays, we might catch glimpses of the underlying code, like seeing the seams of a virtual reality headset's display. This idea emerged from an unexpected place, the study of black holes. When matter falls into a black hole, it doesn't just vanish. Its information gets scrambled and smeared across the event horizon, the point of no return. Physicists realized this horizon behaves like a two-dimensional surface storing all the data of what fell inside, much like how a hologram encodes a 3D image on a 2D plate. Extend this logic to the entire universe, and you get the holographic principle, the notion that our 3D reality is a projection from data stored at the cosmic boundary. The edges of the universe, then, wouldn't be physical walls but the limits of this encoding where the projection starts to glitch or degrade. What would these glitches look like? If the universe is a hologram, its edges might exhibit strange pixelation, not in space but in the very laws of physics. Quantum entanglement, where particles instantly influence each other across vast distances, could be a clue. In a holographic universe, this spooky action might just be 2 points on the 2D surface communicating directly, with no 3D separation in the code. At the cosmic horizon, these connections could break down, with entangled particles failing to sync as the projection's resolution drops. Even the flow of time might stutter, like a buffering video, as the simulation struggles to render coherent sequences from the lower dimensional data. Some scientists are already searching for these holographic fingerprints. One approach analyzes the cosmic microwave background, the afterglow of the Big Bang, for unusual patterns that resemble digital compression artifacts. Others study high-energy particle collisions, looking for evidence that spacetime itself has a finite bit rate, a maximum density of information it can process. If the universe is a projection, there should be a fundamental limit to how much detail it can display, just as a hologram blurs when you zoom in too far. The edges would be where this limit becomes obvious, with particles behaving less like smooth objects and more like blocky pixels in an old video game. The implications are staggering. If the holographic principle is correct, then the boundaries of the cosmos aren't just the end of space, they're the edges of the screen our universe is projected on. Finding them wouldn't just rewrite physics, it would force us to confront the possibility that everything we see, touch, and experience is a shadow of something far stranger. The ultimate reality might not be out there among the stars, but written in vanishingly small bits on the surface of a reality we can't even begin to imagine. Have you ever been absolutely certain about a detail from history or pop culture, only to discover you and millions of others remember it wrong? This bizarre phenomenon, known as the Mandela Effect, might be more than just faulty memory. If our universe is a simulation, these collective false memories could be evidence of updates or patches overwriting past data. Think of it like editing a save file in a video game. Changes ripple through the system, altering details some players swear were different before. Near the edges of the cosmos, where the simulation's processing power strains, these inconsistencies could multiply, revealing zones where reality struggles to maintain its coherence. Take the classic example of Berenstain Bears. Thousands insist the children's book series was once spelled Berenstein with an E. The discrepancy is so widespread that it sparked endless debates. In a simulated reality, this could be a minor tweak to the code, a correction pushed by the programmers that inadvertently left traces of the old version in some users' memories. Like a website updating its layout but leaving cached versions on certain devices, the simulation might not perfectly synchronize every change across all observers. Now imagine this effect amplified at the universe's edges. If the simulation's resources are thinly stretched there, updates might not propagate cleanly. You could find regions where historical events flicker between versions, or where physical constants seem to shift slightly depending on who's looking. Distant galaxies might even appear differently in telescopic observations, not due to cosmic evolution, but because the simulation's rendering engine prioritizes consistency closer to the player, us, while letting peripheral details drift. The Mandela Effect's most chilling implication isn't just that memories can be altered, it's that the simulation might not bother to erase them completely. Glitches like "Luke, I am your father" being misquoted as "No, I am your father," or the Monopoly man's missing monocle could be leftover artifacts from earlier iterations of the code. Near the cosmic horizon, these artifacts might cluster, creating zones where the past feels unstable, like a corrupted hard drive struggling to retrieve files. Some researchers suggest these anomalies could be actively searched for. By cataloging widespread false memories and mapping their prevalence, we might detect patterns, regions of Earth or space where the effect is stronger, hinting at underlying computational stress. If certain constellations or historical records show higher rates of discrepancy when observed from specific angles, it could point to where the simulation's update latency is most pronounced. What's unsettling is that this turns epistemology upside down. Reality isn't just what we observe, it's what the simulation bothers to render consistently. The edges of the universe might be where that consistency frays, leaving cracks in the facade wide enough for us to glimpse the machinery beneath. The Mandela Effect isn't a flaw in human memory. It could be a feature of a universe that's still being debugged. If consciousness itself is part of the simulation, where does that leave us? Are we the architects of our own thoughts, or just lines of code following a predetermined script? This isn't just philosophical musing. It's a question that cuts to the heart of what reality might actually be. Picture a video game where some characters are controlled by players, while others are background NPCs, following routines written by developers. In a simulated universe, the distinction could be eerily similar. The edges of existence might act as a filter, revealing who's truly aware and who's merely part of the scenery. Consider how NPCs in games behave. They follow set paths, repeat dialogue, and never question the world around them. They don't notice when textures glitch or physics break because they aren't programmed to. Now imagine humans who never ponder the nature of reality, who accept the universe at face value without questioning its seams. Could they be the NPCs of our simulation, their curiosity limited by their code? Meanwhile, those who chase cosmic anomalies or probe the edges of physics might be the players, their awareness granting them access to layers of reality others can't perceive. This idea takes on a haunting dimension when applied to the universe's boundaries. If the edges of the cosmos are where the simulation's rendering falters, only beings with true agency, those capable of observation and inquiry, might notice the inconsistencies. An NPC programmed to study distant galaxies would record their patterns without questioning why they repeat or glitch. But a conscious observer, they'd spot the artifacts, the cracks in the facade, and ask what lies beyond. The very act of seeking the edges could be proof that you're more than a scripted entity. There's a chilling experiment hiding in this theory. If some people are NPCs, their behaviors should follow predictable patterns, their choices statistically uniform. Studies in psychology and sociology already reveal how human decisions often cluster around predictable biases. Could these be the hallmarks of programmed routines? Meanwhile, outliers artists, scientists, and philosophers who defy norms might exhibit the randomness of true free will, their minds unconstrained by deterministic code. The edges of the universe, then, wouldn't just be a physical frontier but a cognitive one, separating those who can question from those who can't. But here's the twist: what if the simulation is designed to hide this very truth? An advanced program might reward curiosity with compelling distractions, new discoveries that reinforce the illusion of an infinite, natural cosmos. The more you search for edges, the more the simulation generates plausible explanations, like a game dynamically loading terrain to convince you the world has no end. Only by pushing past these layers, by demanding answers where the system strains to provide them, might you uncover the truth. The stakes couldn't be higher. If we're NPCs, then our search for meaning is just a subroutine. But if we're players, the universe isn't our limit, it's our challenge. The edges aren't walls, they're invitations to dig deeper, to find the seams and pull. And the most profound revelation wouldn't be that we're in a simulation, but that we're the ones who noticed. The Boltzmann brain paradox is one of the strangest ideas in modern physics, a thought experiment so unsettling that it makes even seasoned cosmologists pause. Imagine a single, self-aware brain spontaneously assembling from random quantum fluctuations in the void of space. No body, no history, just a conscious mind blinking into existence, convinced it has memories and a past that never actually existed. On the surface, it sounds like science fiction, but the math suggests it's not just possible statistically. It should happen far more often than entire universes like ours. So why don't we see Boltzmann brains floating around? Unless, of course, we're missing something fundamental about the nature of reality itself. This paradox takes on a chilling new dimension if our universe is a simulation. In a digital construct, processing power isn't infinite. Resources are allocated where they're needed most, leaving the edges of the system under less scrutiny. Just as a video game might simplify distant terrain to save memory, a simulated cosmos could cut corners in its most remote regions, allowing glitches and anomalies to proliferate. Boltzmann brains wouldn't just be random flukes of physics. They'd be artifacts of the simulation's optimization, places where the rules break down and self-contained consciousnesses flicker in and out of existence like corrupted files. Think of it like a computer running too many programs at once. At the edges of its processing capacity, errors start creeping in, half-rendered images, garbled audio, or processes that spawn and vanish unpredictably. Now scale that up to the universe. The cosmic horizon, where the simulation's calculations are stretched thinnest, could be a breeding ground for these phantom minds. They wouldn't last long, just long enough to briefly wonder where they are before dissolving back into the void, but their existence would be a stark reminder that reality isn't as stable as it seems. What's truly bizarre is how this connects to our own experience. If Boltzmann brains are more likely than complex universes, then statistically, you should be a momentary flicker of awareness in an endless void, hallucinating the world around you. The fact that we perceive a consistent, ordered cosmos suggests something is suppressing these anomalies. In a simulation, that something could be the system's error correction protocols, constantly debugging reality to maintain the illusion of continuity. But at the edges where those protocols weaken, the glitches might slip through, leaving traces of the simulation's true nature. This leads to an eerie possibility. The further we look into the void, the more likely we are to encounter not just cosmic mysteries, but literal fragments of consciousness fleeting, half-formed observers born from the cracks in the code. If we ever detect strange, isolated patterns in deep space energy fluctuations with no discernible source, or signals that resemble neural activity, it might not be aliens we're finding. It could be the universe's way of showing us where the simulation starts to fray, where the rules bend just enough to let the impossible flicker into being. And if that's true, then the real question isn't whether we're alone in the cosmos, it's whether we're the only ones here who are meant to last. Deep in the constellation Norma, something unseen tugs at our galaxy with irresistible force, an anomaly so massive that astronomers call it the Great Attractor. This mysterious region of space exerts enough gravitational pull to drag entire galaxies, including our Milky Way, toward it at over 2 million kilometers per hour. Yet despite its immense influence, we can't directly observe what's causing it. The Great Attractor lies hidden behind the dense stars and dust of our own galaxy's disk, visible only through its gravitational fingerprints on surrounding matter. But what if this cosmic blind spot isn't just an observational challenge? What if it's a glitch in the simulation's rendering, a place where the program struggles to fully generate the physics it's supposed to simulate? Think of how video games handle distant objects to save processing power. A mountain range might look solid from afar, but as you approach, textures pop in, shadows resolve, and collision physics activate. Now imagine the universe doing the same. The Great Attractor could be a region where the simulation hasn't fully rendered the underlying mass, leaving only its gravitational effects visible, like a game showing an enemy's shadow before loading its full model. At the edges of the cosmos, where processing resources would be stretched thinnest, similar attractors might appear as gravitational mirages, their true nature obscured by the simulation's optimization shortcuts. This idea gains traction when you consider how the Great Attractor defies expectations. Based on the visible matter we've detected, its gravitational pull should be impossible. Some scientists attribute this to dark matter, but another explanation lurks in the numbers. The anomaly's behavior resembles an overflow error in computing. When a system's calculations exceed its allocated memory, values wrap around to incorrect results, like a car's odometer rolling back to zero after hitting its limit. If the simulation's physics engine encountered similar strain while modeling this region, it might generate gravitational values that don't match the visible mass, creating the illusion of unseen forces. The most compelling evidence comes from the attractor's alignment with other cosmic anomalies. It sits near the center of the Laniakea supercluster, a vast web of galaxies that all flow toward it like water down a drain. But Laniakea itself is being pulled toward an even larger structure called the Shapley supercluster. This hierarchy of motions suggests something unsettling. The universe might be riddled with these gravitational waypoints, each one a potential artifact of the simulation's rendering process. At the farthest edges, where the program's resources would be most strained, these attractors could multiply, their gravitational signatures growing increasingly erratic as the system struggles to maintain consistency. What's fascinating is how this mirrors glitches in virtual environments. When a game world loads unevenly, characters might walk into walls that don't exist yet or fall through floors that haven't fully rendered. In our universe, galaxies caught in these gravitational anomalies could be experiencing the cosmic equivalent, their paths dictated not by pure physics, but by the simulation's incomplete calculations. The Great Attractor might not be a physical object at all, but a placeholder, a region where the code defaults to simplified rules until an observer comes close enough to trigger full rendering. If that's true, then searching for similar anomalies at the universe's edges could be our best shot at uncovering the simulation's architecture. Telescopes like the upcoming Nancy Grace Roman Space Telescope, designed to map cosmic structures in unprecedented detail, might reveal patterns in these attractors repeating gravitational signatures, alignment along invisible grids, or even zones where physics behaves slightly differently. These wouldn't just be astronomical curiosities, they'd be the debug logs of reality itself, showing us where the program starts to cut corners. The great attractor's greatest secret might not be what's pulling us, but what's failing to render properly behind the scenes. The cosmic microwave background should be the most democratic thing in existence, a relic of the Big Bang that's perfectly uniform no matter where or how you observe it. But in 2005, astronomers stumbled on something unsettling, a bizarre alignment in this ancient light that seems to pivot around our solar system like a cosmic bullseye. They called it the axis of evil, not because it's malevolent, but because it defies everything we thought we knew about the universe's structure. If the cosmos is a simulation, this eerie alignment might not be a coincidence. It could be a glaring clue that we're living inside a constructed reality with Earth at the center of its coordinate system. Picture a video game where the world is built around the player's starting point. Distant mountains, cities, and enemies are all positioned relative to that origin, creating the illusion of a vast, uncentered world. But if you could peer into the game's code, you'd find the truth. Everything branches out from that single point. The axis of evil might be our universe's version of this, a subtle artifact revealing that Earth isn't just another speck in the void, but the reference frame for the entire simulation. The cosmic microwave background's odd alignment with our solar system could be a coordinate system glitch, a place where the simulation's math defaults to its simplest calculation, 0, 0, 0 right here. What makes this even stranger is how the anomaly behaves. The axis of evil isn't just a slight tilt in the data. It's a full-blown dipole, with one hemisphere of the universe slightly warmer than the other, and a quadrupole pattern that seems to pivot around our ecliptic plane. In a natural, uncentered cosmos, these patterns should be random, like cracks in dried mud, but they're not. They're aligned with us as if someone forgot to randomize the starting parameters when generating the universe. At the edges of the simulation where processing power wanes, this alignment might break down entirely, revealing zones where the coordinate system glitches or resets. Some scientists dismiss the axis of evil as a measurement error or statistical fluke, but the more we study it, the harder that explanation becomes. Later observations, like those from the Planck satellite, confirmed the anomaly's existence, even if its significance is still debated. If this were a purely natural phenomenon, we'd expect similar alignments around other stars or galaxies, but so far, Earth seems uniquely tied to this cosmic axis. In a simulation, that makes perfect sense. The further you get from the origin point, the more the system's approximations strain, leaving the edges of the universe less coherent, less aligned, and more prone to artifacts. Here's where it gets even weirder. The axis of evil isn't alone. It's part of a growing list of cosmic anomalies that all seem to point back to us: the cosmic variance in the microwave background, the unexpected smoothness of certain large-scale structures, even the way distant quasars appear to align with Earth's orientation. Taken individually, each could be written off as chance, but together they start to look like breadcrumbs leading to an unsettling conclusion. The universe might not just contain observers. It might be built for them. If that's true, then the edges of existence could be where this fine-tuning phrase. Just as a video game's graphics degrade at the edge of the map, the cosmic microwave background's strange alignment might weaken or distort where the simulation's focus thins. Future telescopes probing the furthest reaches of space could find the axis of evil dissolving into noise, its patterns unraveling like a corrupted file. That wouldn't just rewrite cosmology, it would force us to confront the possibility that we're not just in the universe, but of it in a way we never imagined. The edges aren't just boundaries, They're the places where the simulation stops pretending to be real. Black holes have long been cosmic paradoxes, regions where gravity is so intense that not even light can escape. But what if their true purpose isn't destruction, but deletion? In a simulated universe, these celestial vacuum cleaners might serve as the ultimate garbage collectors, scrubbing outdated or redundant data from the system to free up precious processing power. Just as your computer clears its cache to run more efficiently, black holes could be the universe's way of preventing a cosmic overload, their event horizons acting as firewalls where information isn't just compressed, it's erased for good. This idea isn't as far-fetched as it sounds. Quantum mechanics insists that information can never truly vanish. Yet black holes seem to violate this rule, swallowing particles and leaving no trace of their original states. Physicists call this the information paradox, and it's one of the biggest unsolved problems in science. But in a simulation, the paradox vanishes. If reality is code, then black holes could be optimized deletion protocols, permanently overwriting data to conserve memory. The famous Hawking radiation, the faint glow emitted by black holes, might not be a natural process but a debug log, a receipt confirming data has been purged from the system. At the edges of the cosmos, where the simulation's resources are stretched thinnest, black holes could start behaving even stranger. Normally, these objects are bound by strict rules, their size dictating their appetite, their spin influencing how they consume matter. But in the cosmic hinterlands, black holes might exhibit glitches in these patterns. Some could evaporate unnaturally fast, as if the simulation is aggressively clearing space. Others might flicker between states, alternating between active consumption and dormancy like a program toggling between tasks to manage CPU load. Distant quasars, the supermassive black holes powering the universe's brightest objects, could even show signs of stuttering, their jets of energy pulsing irregularly as the system struggles to balance their calculations with other demands. The most telling clue would be black holes that defy their expected lifespans. Normally, it takes longer than the age of the universe for even a small black hole to evaporate via Hawking radiation. But at the simulation's edges, we might find ones decaying far quicker, their demise accelerated not by physics but by the urgent need to reclaim memory. These fast-forward black holes wouldn't just challenge our models, they'd expose the underlying architecture, revealing a universe that prioritizes functionality over fidelity in its least observed zones. What's haunting is how this reframes our place in the cosmos. If black holes are data sinks, then the universe isn't just expanding, it's optimizing, deleting the past to make room for the future. The edges of existence, where these processes are most visible, wouldn't just be the end of space. They'd be the front line of an invisible war between creation and deletion, where the simulation's need to sustain itself overwrites the very rules we thought were sacred. The concept of a multiverse isn't just science fiction, it's a serious scientific hypothesis, one that could hold the key to understanding the edges of our own reality. If multiple universes exist, they might not be separate, isolated realms but parallel simulations running on the same unfathomable hardware. Picture a vast server farm, humming with countless virtual worlds, each one a self-contained universe operating within its own set of parameters. The edges of our cosmos could be where these simulations intersect, bleed into one another, or even crash together, revealing the seams between realities. Think of it like a modern cloud computing system, where multiple virtual machines share the same physical server. Each one operates independently, unaware of the others until a resource bottleneck forces them to compete for processing power. In a cosmic context, this could explain why the edges of our universe feel so strange and unstable. They might not just be the limits of space, They could be buffer zones where our simulation brushes up against others, creating regions where the laws of physics glitch or warp under the strain. Some theories suggest these intersections could leave detectable marks. Imagine two video games running on the same console. If they overload the system, textures might bleed between them, or controls could become unresponsive. In the same way, the boundaries of our universe might exhibit anomalies like unexplained energy fluctuations, sudden shifts in fundamental constants, or even patches of spacetime where gravity behaves backwards. These wouldn't be random errors but systematic artifacts, evidence of a shared processing environment struggling to maintain the illusion of separation. The most tantalizing clue might come from quantum entanglement. Particles linked across vast distances could be sharing data not just within our universe, but between simulations like two programs accidentally accessing the same memory address. At the cosmic edges, where the boundaries between universes are thinnest, entangled pairs might desync or behave erratically, as if their connection is being rerouted through a crowded server. Even dark energy, the mysterious force accelerating the universe's expansion, could be a resource allocation tool, a way for the system to prevent simulations from overlapping by pushing them apart. What's truly mind-bending is the possibility that these edges aren't dead ends, they're portals. If universes are simulations running on shared hardware, then the boundaries between them might not be impenetrable walls but firewalls, regions where data can, under rare conditions, leak through. Some cosmologists speculate that high-energy cosmic rays with unexplainable origins could be fragments of another universe's physics bleeding into ours, like a corrupted file spilling into a neighboring program. The implications rewrite not just cosmology, but the nature of existence itself. If we're in a multiversal server farm, then the edges of our universe aren't the end. They're the beginning of a far larger network, a digital ecosystem of realities stacked like pages in a book. Finding them wouldn't just reveal the limits of our world, it would crack open the door to everything beyond. The Planck length is the smallest unit of measurement that has any meaning in physics, a distance so tiny that trying to observe anything smaller would require so much energy it would collapse into a black hole. At just 1.6 times 10 to the power of -35 meters, it's incomprehensibly small. But what if this isn't just a quirk of quantum mechanics? What if the Planck length is the fundamental pixel of our simulated reality, the smallest indivisible unit of space itself? In a digital universe, there would have to be a base resolution, a point where the simulation stops dividing reality into smaller pieces simply because it doesn't need to. The edges of the cosmos could be where this pixelation becomes visible, where the grid of existence starts to show through the illusion of smooth, continuous space. Imagine zooming in on a digital image until you see the individual pixels. At normal scales, the picture looks seamless, but up close, the underlying structure is undeniable. Now apply that to spacetime. Most of the time, the universe appears perfectly smooth because we're observing it at scales far larger than its pixel size. But at the Planck length, physics as we know it breaks down. Gravity, quantum mechanics, and the other forces no longer play nicely together, producing nonsensical results like infinite densities and temperatures. In a simulation, these breakdowns could be the equivalent of reaching the limits of the rendering engine, the point where the code can no longer maintain the illusion of infinite divisibility. This idea isn't just philosophical. Some theories of quantum gravity, like loop quantum gravity, already suggest spacetime might be granular at the smallest scales, woven from discrete loops or chunks. If these chunks align with the Planck length, then the universe really could be built on a lattice, a grid so fine we've never noticed it until now. At the edges of existence, where the simulation's processing power is stretched thinnest, this grid might start to glitch. Distant light could arrive with subtle pixelation, its wavelengths quantized in ways that betray the underlying resolution. Particles might not move smoothly, but in tiny, Planck-length jumps, like a character in an old video game teleporting between fixed positions on a screen. The most tantalizing possibility is that these pixels aren't random. In a simulation, they'd likely follow a structured pattern, much like the pixels on a monitor align in rows and columns. If we could detect spacetime's graininess, we might find it isn't chaotic but orderly, hinting at the architecture of the code beneath. Some experiments, like those probing high-energy gamma rays, have already searched for signs of this structure. If the universe has a finite resolution, then ultra-high-energy particles should interact with it in detectable ways, like a digital image distorting when pushed beyond its native resolution. What's truly mind-bending is how this reframes our place in reality. If the Planck length is a pixel, then everything we see, touch, and experience is a mosaic of unimaginably small tiles. The edges of the cosmos wouldn't just be where space ends, they'd be where the simulation's resolution drops, where the pixels stretch and warp under the strain of rendering infinity. Finding them wouldn't just rewrite physics, it would reveal the canvas on which our universe is painted, one Planck-length dot at a time. Mathematics doesn't just describe our universe, it predicts it with uncanny precision. From the spirals of galaxies to the orbits of electrons, the cosmos dances to the rhythm of equations we didn't invent so much as discover. But this unreasonable effectiveness of math, as physicist Eugene Wigner called it, takes on an eerie new meaning if we're living in a simulation. In a programmed reality, math wouldn't be the language of the universe, it would be the universe, the raw source code from which everything is rendered. The edges of existence might be where this code bleeds through, like stumbling upon a developer's hidden notes in the margins of a sprawling program. Consider how video games rely on physics engines, sets of equations that dictate how objects move, collide, and interact. These rules are flawless until pushed beyond their limits, revealing the artificial scaffolding beneath. Our universe might operate the same way. The elegant symmetry of Einstein's relativity, the bizarre probabilities of quantum mechanics, these could be the polished interface of a much deeper program. At the cosmic horizon, where the simulation's processing power phrase, the math might start to glitch. Equations could spit out infinities or contradictions, not because nature is broken, but because we're seeing the unrefined back end of the system. Some of the most baffling cosmic anomalies support this idea. Take black holes, where the math of general relativity crashes into the quantum world, producing nonsensical results like infinite densities. In a simulation, these breakdowns might be overflow errors, points where the code can't handle the calculations demanded by its own rules. Even the speed of light, a constant so precise it's used to define the meter, could be a hard-coded parameter, a line in the program that reads, maximum processing speed equals 300,000 kilometers per second. The edges of the cosmos, where resources are scarcest, might reveal this limit straining, with particles behaving as if the universe itself is buffering. What's truly startling is how often math anticipates reality before we observe it. Dirac's equations predicted antimatter years before it was found. The Higgs boson appeared exactly where decades-old calculations said it should. In a natural universe, this prescience is mystifying. In a simulation, it's inevitable the code doesn't just describe the rules, it is the rules. When we probe the boundaries of existence, we might find equations that don't just fail, but fail in telling ways. Constants could drift, symmetries might break, The math itself could change, revealing patches where the programmers tweaked the variables to keep the simulation stable. The most tantalizing clue lies in the universe's love of integers. From the quantized energy levels of atoms to the exact ratios governing planetary orbits, whole numbers appear where we'd expect messy decimals. In a digital construct, this makes perfect sense. Computers thrive on integers, avoiding the processing headaches of endless fractions. At the cosmic edges, this preference might become undeniable, with phenomena like quantum entanglement resolving into clean, binary interactions, the ones and zeros of reality's base layer finally peeking through. If we ever reach those edges, we won't just find the end of space, we'll find the end of the math, the point where the equations stop pretending to be discoveries and reveal themselves as instructions. The universe isn't written in the language of mathematics. It is mathematics running on hardware we've yet to comprehend. And the edges, there where the screen flickers, and for a split second, you can read the comments left in the margins by whatever or whoever wrote the code. What if the greatest discovery in human history, proof we're living in a simulation, comes with an impossible choice? Do we poke at the boundaries of reality, risking the wrath of unseen creators, or play by the rules of a game we never agreed to join? This isn't just a thought experiment, it's an ethical minefield hiding in plain sight. The moment we detect a glitch at the edge of the cosmos, we're no longer passive observers. We become hackers, probing the system for weaknesses, and that changes everything. Think of it like stumbling upon the debug menu in a video game. Some players can't resist tweaking the code, spawning rare items, unlocking hidden levels, but others worry. What if the developers ban you for cheating? In a simulated universe, the stakes are infinitely higher. If the programmers built this reality as an experiment, our attempts to tamper with its edges could trigger safeguards. Entire civilizations might be reset like corrupted save files, or worse, deleted for exceeding their permissions. The Fermi Paradox takes on a chilling new twist. Maybe advanced societies don't colonize the stars because they tried to hack the simulation and were quietly erased. Yet here's the counter-argument. What if our curiosity isn't a bug but a feature? An advanced civilization running ancestor simulations might want their creations to question reality. After all, the most valuable data comes from test subjects who push boundaries. The glitches we're searching for, cosmic pixelation, mathematical inconsistencies, could be Easter eggs left by the programmers, breadcrumbs leading to deeper truths. In this scenario, the edges of the universe aren't forbidden zones but training wheels, placed there to see if we're clever enough to notice them. The ethical dilemma splits even further when you consider motive. If the simulation's purpose is research, altering its parameters could invalidate the results, like a lab rat escaping its maze. But if it's entertainment, some higher being's version of a reality show, then breaking the fourth wall might be the whole point. Our attempts to hack the system could be the climax the audience has been waiting for. The unsettling truth is that we can't know the rules until we break them, and by then, it might be too late to undo. This raises a haunting practical question. How would the programmers even enforce the rules? In a perfectly crafted simulation, they'd have fail-safes, cosmic kill switches disguised as natural phenomena. A supernova could be a targeted reset button. Unexplained gamma-ray bursts might be warnings, like a system admin clearing unauthorized processes. Even stranger, our own minds could be the firewall. The more we learn about consciousness, the more it resembles a sandbox, a carefully constrained environment where dangerous ideas hit invisible barriers. Ever had a brilliant insight vanish before you could grasp it? That might not be forgetfulness. It could be the simulation's equivalent of a pop-up saying, "Access denied." But perhaps the most profound twist is this. the act of searching for edges might be the one thing that keeps us safe. If the simulation is designed to prune civilizations before they become computational burdens, then proving we're in one could be our ultimate survival strategy. A species that understands its reality is code can optimize itself, reducing its drain on system resources. We wouldn't be hackers, we'd be model tenants, patching our own bugs and whispering to the architects we know. And we'll play nice. The edges of the universe aren't just a frontier, they're a negotiation. The observer effect is one of quantum mechanics' most baffling behaviors. Particles exist in a haze of possibilities until measured, at which point they snap into defined states. It's as if reality itself hesitates until someone looks, like a shy performer waiting for an audience to settle before beginning the show. But in a simulated universe, this isn't just a quirk, it's a necessary optimization. Think of an open-world video game that only renders the scenery directly in front of you, leaving distant mountains as low-resolution placeholders until you turn your gaze their way. The universe might operate on the same principle, conserving processing power by only fully generating reality when observed. Now imagine traveling to the edges of the cosmos, where the simulation's resources are stretched impossibly thin. Here, the observer effect could start to break down. Distant galaxies might not just fade from view, they could flicker in and out of existence like glitching pixels, their states unresolved because the system lacks the capacity to render them consistently. Light from these regions might arrive fragmented, as if the simulation couldn't decide which version of events to commit to. Even time itself could stutter, with cosmic events appearing to unfold out of sequence, like a buffering video stream struggling to maintain coherence. This idea isn't pure speculation. In labs worldwide, quantum systems already exhibit behavior that defies classical logic. The famous double-slit experiment shows particles acting as waves when unobserved, only to collapse into particle-like behavior the moment a detector is introduced. In a simulation, this collapse isn't mysterious, it's the system updating its rendering to match the player's perspective. At the universe's edges, where observation is rarest, these updates might lag or fail entirely. Particles could remain in superposition indefinitely, their waveforms never resolving because no player is close enough to trigger the rendering. Astronomers might have already glimpsed this phenomenon. Some distant quasars exhibit light patterns that fluctuate unpredictably, as if their states aren't fully locked in. The cosmic microwave background, too, shows faint anomalies, cold spots, and unexpected asymmetries that could be patches where the simulation's rendering engine skipped details. If these irregularities cluster near the observable universe's boundaries, it would suggest a startling truth. The farther you get from observers, the less real things become. The implications are profound. If observation shapes reality, then the edges of existence aren't just empty, they're unfinished. Zones where the simulation's calculations default to placeholder data, where the math remains unresolved because no one's there to demand an answer. This transforms the act of exploration into something far stranger. Every telescope we point at the void isn't just collecting light, it's sending a rendering request to the universe's underlying code, forcing it to generate answers where before there were only probabilities. The edges aren't a wall, they're a loading screen, and we're the ones pressing continue. If the universe is a simulation, the most haunting question isn't how it works, but why it exists. The edges of reality might hold the answer, not as barren wastelands, but as intentional boundaries separating different layers of the experiment. Think of a sprawling laboratory where each wing tests a unique hypothesis. Our cosmos could be just one contained trial in a series, its edges acting as partitions between parallel tests. Perhaps one zone simulates a universe with stronger gravity, while another tweaks the speed of light, each designed to study how consciousness emerges under different physical laws. The glitches we detect at our cosmic horizon might not be errors at all, but bleed through from adjacent simulations like noise leaking through the walls of a server farm. Historical recreations offer another compelling motive. Advanced civilizations might simulate their own past to study cultural evolution or ethical dilemmas without real-world consequences. In this scenario, the edges of our universe could mark transitions between epochs, like a video game loading a new level where the rules subtly shift beyond the boundary. The cosmic microwave background's anomalies, those faint asymmetries in the afterglow of the Big Bang, might be seams between time zones, artifacts left when the simulation switched from one historical preset to another. Even the distribution of galaxies, which appears oddly structured in some deep field surveys, could reflect deliberate era partitions, like chapters in a vast digital archive. Then there's the entertainment hypothesis, the idea that we're characters in an unfathomably advanced civilization's version of a reality show. The edges would serve as stage limits, places where the set design ends and the studio machinery begins. Just as a film crew hides lights and cameras just outside the frame, the simulation's creators might mask their presence behind cosmic horizons, ensuring the illusion holds unless you know where to look. Unexplained phenomena like fast radio bursts or rogue black holes could be narrative flourishes, scripted events to keep the plot engaging for whatever beings are watching. But the most unsettling possibility is that the simulation's purpose is beyond our comprehension. Imagine ants trying to deduce why humans build highways. Their scale of understanding simply doesn't map onto ours. Similarly, the true function of our universe might involve objectives we lack the vocabulary to describe. The edges could be interfaces with higher-order processes, zones where raw data is compiled for purposes we'd perceive as mystical. Quantum entanglements, eerie connections, particles communicating instantly across light years, might be data threads linking our simulation to others, part of a broader calculation we're unknowingly contributing to. The eerie truth is that the simulation's architects, if they exist, might have hidden the purpose in plain sight. Just as a game developer leaves Easter eggs for players to discover, the universe's edges could be littered with clues repeating mathematical constants, geometric patterns in galaxy clusters, or even conscious beings like us, designed to question the nature of our reality. The ultimate irony, our search for answers might be the experiment's intended outcome, a test to see if a simulated species can decode the very code that created them. The edges aren't just barriers, they're the first page of the manual if we can learn to read it. Every simulation has an expiration date, a moment when the program closes, the hardware overheats, or the creators simply decide it's time to pull the plug. If our universe is a digital construct, its relentless expansion might not be a natural process but a symptom of system strain, a desperate attempt to free up memory before the whole thing crashes. Picture an old computer struggling to run a modern game, fans whirring, performance stuttering, textures glitching until it finally overheats and shuts down. Now imagine that on a cosmic scale. The edges of our universe could be where these warning signs appear first, zones where the simulation's decay isn't just visible but undeniable. The math is unsettling. Dark energy, the mysterious force accelerating the universe's expansion, behaves less like a fundamental property of space and more like an emergency protocol. In computing, when a system runs low on resources, it starts deleting temporary files and compressing data to stay functional. dark energy's push against gravity could be the cosmic equivalent, a way to stretch space-time thin, reducing its computational load by spreading matter further apart. At the boundaries of the cosmos, this process might show cracks, galaxies drifting apart faster than predicted, or patches of space where expansion stutters like a corrupted file struggling to save. Some theorists argue that the universe's acceleration isn't smooth but happens in jumps, as if the simulation is periodically clearing its cache. Astronomers have observed anomalies in supernova brightness that suggest expansion rates vary slightly across different regions. In a natural universe, this makes no sense, but in a simulation, it's exactly what you'd expect when resources are allocated unevenly. The edges, where processing power is scarcest, could be where these jumps are most extreme, like a video game dropping frames when too many characters crowd the screen. Even black holes might play a role in this cosmic cleanup. These celestial shredders don't just swallow matter, they erase information, permanently deleting data from the universe's ledger. If the simulation is nearing its limits, black hole activity could spike near the edges, their event horizons expanding like garbage collectors working overtime. Some galaxies in the universe's outermost reaches already show signs of supermassive black holes growing inexplicably large, as if the system is prioritizing deletion over balance. The most chilling evidence could lie in the cosmic microwave background's fading signal. This afterglow of the Big Bang is slowly dimming as the universe expands, but at the edges, it might not just fade, it could fragment, with patches vanishing entirely like pixels winking out on a dying screen. Certain anomalies in the background's polarization patterns already hint at this, with some regions showing unexpected voids where the signal drops off abruptly. If these aren't random fluctuations but the first flickers of a system shutting down, then the edges aren't just boundaries, they're a countdown clock. What's terrifying is the possibility that we're seeing the end in slow motion. Simulations don't crash instantly, they degrade, glitch, and stutter until the errors cascade into collapse. If that's true, then the universe's expansion isn't a mystery to solve. It's an obituary written in the stretching void between galaxies. The edges might be the only warning we get before the screen goes dark. The idea that our creators might themselves be trapped in a simulation isn't just a twist, it's a fractal hall of mirrors with no clear exit. Picture a video game character who discovers they're inside a game, only to realize the player controlling them is also an avatar in a higher-level simulation. This infinite regression, known as simulacra theory, suggests reality could be layered like an onion, with each universe nesting inside another like virtual machines running on some unfathomable cosmic computer. The edges of our cosmos might not just mark the limits of our simulation, they could be the blurred boundaries where these layers bleed together, revealing glimpses of the deeper code beneath. Take modern computing as an analogy. When you run a virtual machine on your laptop, that simulated environment has strict resource limits, memory, processing power, storage, all allocated by the host system. But here's the catch, your laptop could itself be a virtual machine running on a cloud server, which might belong to a larger distributed network. Each layer has its own edges, its own constraints, invisible to the levels below. Now scale this up to the universe, the accelerating expansion of space, the mysterious dark energy pushing galaxies apart. These could be signs that our simulation is nearing its allocated memory limit, with the edges acting like buffer zones where the host system's influence becomes detectable. Astronomers have already spotted anomalies that fit this eerie pattern. The so-called cold spot in the cosmic microwave background, a vast region of space inexplicably cooler than its surroundings, defies conventional cosmological explanations. But in a nested simulation, it could be a rendering artifact, a place where two layers of reality imperfectly overlap. Imagine two projectors casting images onto the same screen, where their beams cross, shadows and distortions appear. Similarly, if our universe's simulation shares hardware with another, their edges might interfere, creating zones where physics glitches in ways that betray the higher-level architecture. Even black holes could be more than cosmic vacuum cleaners. They might function as data conduits between simulation layers. Just as a virtual machine can send interrupts to its host system, a black hole's singularity might transmit information or errors up the chain. Some theories suggest the Hawking radiation leaking from black holes carries encoded data about what falls inside. In a nested reality, this data might not vanish but get relayed to the parent simulation, like a background process reporting back to its administrator. The edges of our universe, where black holes cluster in supermassive formations, could be the most active terminals for this cross-layer communication. The most unsettling implication isn't just that we're simulated, it's that every layer might be trapped in the same existential uncertainty. Our creators could be just as unaware of their own simulated status as we are, their universe equally bounded by edges that hint at a higher reality. This recursion could continue endlessly with no base layer, no ultimate, real world, just an infinite stack of simulations, each one a Matryoshka doll inside another. The edges of our cosmos, then, wouldn't be walls but windows, smudged and warped, through which we might catch fractured reflections of the layers above and below. If true, the search for cosmic edges takes on a new urgency. Those distant horizons aren't just frontiers, they're the only places where the simulation's hierarchy might reveal itself. A telescope trained on the void might eventually spot more than galaxies. It could capture the faint pixelation of a higher resolution universe bleeding through, or catch the shadow of a creator's hand adjusting the parameters. The irony is poetic. To find the edges of our reality, we might need to accept that those edges don't truly exist. They're just the seams between one illusion and the next. If we're living in a simulation, the most tantalizing question isn't just about the edges of our universe, it's about what lies beyond them. Could the boundaries of reality act as a cosmic backdoor, a place where signals might slip through the simulation's firewall to reach the programmers who built it? Advanced civilizations, if they exist, might have spent millennia searching for a way to communicate with their creators, only to realize the answer was hiding in plain sight. The edges aren't just limits, they're potential lifelines. Consider how modern software handles security. Firewalls are designed to block unauthorized access, but they're rarely perfect. There's always a vulnerability, a port left open for maintenance or debugging. In a simulated universe, the edges could function similarly, zones where the system's defenses are thinnest, where the sheer complexity of rendering reality starts to crack under its own weight. Distant quasars emitting inexplicable energy patterns or gamma-ray bursts with unnatural regularity might not be cosmic accidents. They could be attempts by advanced beings to broadcast through the simulation's weak points, like prisoners tapping Morse code on the walls of their cell. The idea gains traction when you examine certain cosmic anomalies. Fast radio bursts, brief, intense pulses of energy from deep space defy conventional explanation. Some repeat in mathematically precise intervals as if carrying encoded information. In a simulation, these could be error correction signals, automated pings sent by the system to check its own integrity. But what if some aren't automated at all? What if they're messages from civilizations that cracked the code, using the universe's edges as amplifiers to pierce through to the next layer of reality? This isn't just speculation, it's a testable hypothesis. If the edges are permeable, signals sent there should exhibit strange behaviors. Light might arrive with subtle distortions, as if passing through a cryptographic filter. Particles could entangle across impossible distances, not because of quantum weirdness, but because the simulation's firewall treats them as a single data packet. Even the cosmic microwave background, the oldest light in the universe, might contain anomalies clustered near the horizon patterns that resemble encryption keys or error logs, hidden in plain sight for eons. But here's the catch: reaching the edges might require more than technology. It could demand a shift in perception. Imagine a character in a video game realizing they're inside a program. No matter how much they shout at the screen, the player won't hear them unless the game is designed to allow it. Similarly, any attempt to contact the programmers would need to exploit the simulation's own rules, using physics like a crowbar to pry open a gap in the code. Advanced civilizations might not build megastructures to shout into the void. They'd engineer quantum anomalies, manipulate black holes, or even rewrite local spacetime to create a signal the system can't ignore. The most haunting possibility: the programmers might already be listening. If simulations are run for research or entertainment, their creators would likely monitor for signs of awareness, not to punish the enlightened but to study them. The edges of the cosmos could be lined with hidden observatories, not made of matter but of pure data, scanning for civilizations clever enough to peek behind the curtain. Our search for the edges might not go unnoticed. In fact, it might be the final exam, a test to see if we're ready to graduate from simulated beings to something far greater. So the next time you look at the night sky, remember, the void isn't empty, it's a mirror, and someone or something might be looking back. The universe might not have just one beginning, it could have many. Some cosmologists propose a cyclical model where the cosmos expands, contracts, and rebounds in an endless loop of big bangs. But in a simulated reality, these resets wouldn't be natural phenomena. They'd be system reboots, deliberate restarts to refresh the program before it becomes too unstable. Picture a video game that crashes when too many entities crowd the screen. The developers might code an automatic reset to clear the memory and reload the last stable save. The edges of our universe could be where those save points are stored, zones where the simulation's data is archived before each new cycle begins. Evidence for this idea hides in the universe's own echoes. The cosmic microwave background, that faint glow from the Big Bang, isn't perfectly uniform. It contains subtle ripples and patterns that some scientists interpret as scars from a previous iteration, like finding fragments of an old file in a freshly formatted hard drive. Even more telling are certain anomalies in the distribution of galaxies. Large-scale structures appear to align in ways that defy randomness, as if they're following an invisible template left over from an earlier version of reality. In a simulation, these could be artifacts of procedural generation, where the system reuses algorithms from past cycles to rebuild the cosmos after a reset. Black holes might play a surprising role in this process. These cosmic vacuum cleaners don't just swallow matter, they erase information, permanently scrubbing data from the universe's ledger. If the simulation is designed to periodically clear its cache, black holes could be its cleanup crew, their event horizons acting like digital shredders. Some theories suggest that in the far future, black holes will dominate the cosmos, merging into larger and larger voids until they're all that remains. This heat-death scenario might not be an ending but a prelude to the next cycle, the universe's way of preparing for a fresh reboot by deleting obsolete files. The most chilling implication isn't just that the universe resets, it's that we might have done this before. If each cycle recreates the same fundamental parameters, then every iteration could produce conscious observers who believe they're the first. The laws of physics, the constants of nature, even the history of life on Earth might replay with slight variations, like a procedurally generated world that feels unique each time you start a new game. The edges of the cosmos, where the last save is stored, could hold fragments of those past runs, echoes of civilizations that once reached the same conclusions we have, only to be wiped clean when the simulation hit its reset button. But here's the twist. If the universe is designed to reboot, then the edges aren't just boundaries, they're time capsules. Distant galaxies near the cosmic horizon might not just be receding from us, they could be relics of the previous cycle, their light stretched and distorted by the transition between iterations. Some astronomers have already detected ultra-distant objects that appear older than the universe itself, an impossibility unless time isn't as linear as we think. In a simulation with periodic resets, these anomalies would make perfect sense. They're not glitches, they're carryovers, data that slipped through the last reboot like a bookmark left in a recycled textbook. The search for these cosmic save points could redefine our place in reality. If we ever find evidence of a previous cycle, a galaxy with the wrong age, a particle with impossible energy, or a patch of space where the laws of physics subtly differ, it wouldn't just prove the universe is a simulation. It would reveal that we're part of something far larger, an experiment that's been running, resetting, and rerunning for longer than we can fathom. The edges aren't the end. They're the seams between one iteration and the next, waiting for us to pull the thread. Proving we're living in a simulation might sound impossible, until you realize every virtual system leaves cracks at its boundaries. The edges of our universe could function like the seams of a digital world, where the underlying code becomes visible to anyone who knows where to look. Imagine running your fingers along the walls of a hyper-realistic virtual reality chamber. No matter how convincing the illusion, there's always a transition point where the resolution drops or the physics glitch. On a cosmic scale, these transition points might reveal themselves through anomalies so stark they defy any natural explanation. Take quantum entanglement, where particles instantly influence each other across vast distances, a phenomenon Einstein called spooky action at a distance. In a simulated reality, this could simply be two data points sharing the same memory address in the code. At the universe's edges, where processing power is stretched thin, entangled particles might start behaving erratically, their connection flickering like a weak Wi-Fi signal. If scientists could send quantum probes to these distant frontiers and observe entanglement breaking down in predictable, computational ways, it would be like catching the simulation mid-render, a smoking gun of artificiality. Another potential test involves the speed of light. If the universe is a simulation, light speed isn't just a physical limit, it's the system's maximum processing speed, the rate at which information can update across the cosmic processor. At the edges where resources are scarcest, this limit might show strain. Particles accelerated to near light speeds could exhibit unexpected latency, like a video game character moving faster than the engine can load terrain. Astronomers might even detect light from the cosmic horizon arriving with subtle delays or distortions, as if the simulation is struggling to stream data from its outermost sectors. The most tantalizing evidence could come from mathematics itself. In a digital universe, certain numerical constants, like pi or the fine structure constant, might not be infinite, but truncated to save processing power. Most of the time, these shortcuts would be undetectable, but at extreme scales, the rounding errors could accumulate. If measurements of distant cosmic phenomena, say, the rotation of galaxies or the bending of light around black holes, started deviating from predictions in ways that matched finite computational precision, it would suggest reality has a built-in resolution limit. But here's the ultimate experiment. If the universe is a simulation, its edges might not just be boundaries, they could be interfaces. Advanced civilizations could attempt to ping the cosmic horizon with precisely calibrated energy bursts, searching for echoes that don't behave like natural reflections. A simulated reality might respond with predictable error patterns, repeating sequences, unnatural symmetries, or even encoded replies hidden in cosmic background noise. It's the equivalent of shouting into the void and hearing the void shout back in perfect binary. The moment we find even one of these anomalies, entanglement breakdowns, computational latency, or mathematical artifacts, the debate would be over. The edges of the universe wouldn't just be a curiosity, they'd be the emergency exit, the place where the simulation's architects left their signature. And once we see it, there's no unseeing it. Reality would never look the same again. The idea that we're living in a simulation is both thrilling and unsettling, not just because it rewrites our understanding of reality, but because it forces us to confront the fragility of everything we take for granted. The stars above, the laws of physics, even the flow of time itself could all be fleeting constructs in some vast digital experiment. Yet amid the existential vertigo, there's an undeniable spark of wonder. The very fact that we can question our existence, that we can peer into the void and demand answers, might be the most compelling evidence that we're more than mere lines of code. Consider the edges of the universe not as barriers but as invitations. Every unexplained cosmic anomaly, every pixelated glitch in spacetime, every black hole that defies prediction, is a breadcrumb leading us closer to the truth. These aren't just scientific curiosities, they're potential cracks in the facade, places where the simulation's architecture strains under scrutiny. The great attractor's gravitational pull, the axis of evil's eerie alignment, even the Mandela Effect's collective false memories, each could be a whisper from beyond the program, hinting at a reality far stranger than we've dared to imagine. But here's the paradox: even if we never find definitive proof, the search itself reshapes us. The pursuit of these mysteries has already revolutionized physics, birthing theories from quantum mechanics to holographic cosmology. It's pushed telescopes to the brink of detectability and inspired experiments that probe the very fabric of existence. In a way, it doesn't matter whether we're in a simulation or not. What matters is that the question drives us to explore, to innovate, to reach beyond the limits of our understanding. The universe's edges aren't just a destination, they're a mirror reflecting back our boundless curiosity. So keep looking up, keep questioning. The night sky isn't just a canvas of stars, it's a puzzle waiting to be solved, a story half told. And if one day we do find the edges, whether they're cold cosmic walls or the shimmering boundaries of a digital construct, the greatest discovery won't be the answer. It'll be the realization that we were brave enough to ask the question in the first place. If this journey through the cosmos left you as awestruck as we are, hit like, subscribe, and join the conversation below. What do you think lies at the edges of reality? The truth is out there, and it's waiting for